Welcome to the Chapter 10 Part 2 video. This is 10.7 and kind of a conglomeration that we have made of circles. So it takes into account some parts of Chapter 10, some parts of Chapter 12. This cannot be found in the online book. So the circles section is unique to our notes packet. So for our last section of Chapter 10 proper is area of a circle. And so all of the circle notes will be together in this video. And our objective for this section, which is just this one half page, is to find the area of a circle. The area of a circle uses the product of pi. This is pi. You say it the same as pi. And pi equals about 3.14. I should put approximately. You find pi on your calculator above the little exponent sign below the clear. So to type pi into your calculator, you'll do secant, remember it's like your shift key, and then right here the little pi. And you'll see if you hit enter, it's 3.1415926. And the thing about pi, it's irrational, it never ends. So when we approximate using pi, we will just use 3.14. Okay, so the area of a circle, we use pi times the radius squared. What does that mean? Well, if we're looking at a circle, we have the radius. A radius squared would be this little square. If I have 2 of those, that would be 2 times the radius squared. 3 of them would be 3 times the radius squared. And if I take all of this stuff that's outside of those, outside of the circle, and I fill it in here, there's still a little bit more room, and that's why it's 3.14. Okay, so it's 3 and a little bit more. 3.14 times the radius squared. If you want to see what this looks like in terms of the diameter, it's a little bit tricky because if we substitute, remember diameter is 2 times the radius. Diameter goes all the way across the circle. A radius is just from the center out to the edge of the circle. And so if we wanted to write this in the diameter, we'd have to use half of the diameter for the radius. So we can say that area is pi times the diameter over 2 squared, which we can say is about 3.14 diameter squared over 4. So it's a little bit less than the diameter squared. So if I were to draw that as a picture, here's my circle. Here's my diameter. The diameter squared would make this whole big box all the way around the circle. So see how it's a little bit less than the diameter squared, but more than 3 times the radius squared. So we use pi r squared for the area. So we want to find the area of the wrestling mat here. We have 32. 32 represents that whole white line. That is a diameter. In order to calculate our area using pi r squared, we need to find the radius. If the diameter is 32, the radius will be half of that, which is 16. Whoops, 16. Substitute that into the equation, pi times 16 squared. Now it is important of how you type this into your calculator because we don't want to square pi, just the 16. So when we type this, we're going to put pi times 16. And you have 2 options. You can use this little x squared button, or you can use the exponent 2. So I'm going to use the squared button. So it should be pi times 16 squared. No parentheses, enter. And then we'll round to 2 decimal places. So 804.25 is approximately 804.25. Double check, it doesn't say round to the nearest anything. This is an area, so it's feet squared. The reason I chose 2 decimal places is because pi, we usually represent to 2 decimal places. So that's a safe place to round when we're rounding our areas. I'd like you to try these 2 examples using the a equals pi r squared formula. For part A, we're given the radius. The radius is 3. Area equals pi r squared. Pi times 3 squared. If I want to write the exact answer, so in the one above we rounded, And if you round it for this, that's absolutely fine. If I wanted to leave this exact, it says leave answer in terms of pi. That means we're going to do 3 squared, which is 9. So pi times 9. We'll write the number first. That will be 9 pi. I should put units, yards squared. 9 pi yards squared, which is approximately, into the calculator, we can just do 9 pi. It will automatically know that that's multiplication, 28.27. 28.27 square yards. But because it says in terms of pi, this should be the answer. If you put this, that's absolutely fine. For part B, again, we're given a diameter. The diameter is 2/3. The radius is half of that. Half of 2/3 is 1/3. Area equals pi r squared equals pi times 1/3 squared, which is 1/9 pi. We can write that as pi over 9. That is the simplified version, and our units are square inches. Okay, let's take a look at the next page. Okay, so we're looking at a few more vocabulary terms for circles. We've already talked about a lot of these previously, but we want to formally define them. So a circle is the set of all points that are equidistant, meaning same distance from a given point, and that given point is called the center. So if we think back to when we were doing constructions, the center is where you would put the point of your compass, and all of the points that are the same distance create that circle. The diameter is the segment that passes through the center and has 2 endpoints on the circle. The radius is the segment with 1 endpoint on the circle and the other endpoint at the center. The central angle is the angles whose vertex is at the center. Some new vocabulary terms. So if we're looking at, let's take a look at what these look like graphically. So if we're looking at the circle is all of the points that are equidistant from point C. The diameter is AB. AB is a diameter. CD is a radius. And the central angle we can say is BCD or DCA. Angle BCD or angle DCA are both central angles. We can also say that BCA is a central angle, but we would almost always just call that the diameter because it's a straight angle. Angle BCA. It's still central because it goes through that center point. So a semicircle, back to the definitions, a semicircle is half of the circle. Semi means half. So half of the circle, meaning cut it right down the diameter. We have 1/2 on this side and we have 1/2 on this side. A minor arc is any arc smaller than the semicircle. Smaller. And a major arc is any arc that is longer or larger than a semicircle. So a semicircle would be A to B, and because it is not a straight line, we put an arc over it. A minor arc would be A to D or D to B, A to D or D to B, because those are both less than half of a circle. A major arc would be D to B to A. And for a major arc, we need all 3 points because I could go from D to A the short way, but a major arc has to go the long way. So from D to B to A. And those 3 letters are what tell us that this is a major arc. Okay, so some ways that lines can intersect with the circles. If we have a segment with 2 endpoints on the circle, so it could be a diameter. It could also be the segment from C to D, for example, on the second diagram. That is called a chord. Like a rope is a chord. This is a chord that goes from C to D. with endpoints, so no arrows on that. A line segment that intersects the circle in only one point, that would be line D. Here, let's call it line L, because there are two lines that go through point D. So this is, our example is line L. That is called a tangent. And it is related to tangent from trigonometry. A line that intersects the circle at 2 points, so the line that goes through CB, is called a secant. So that would be CB with arrows. The line is the secant. Let's look at some applications for this. If we have a central angle, we know that the angle measure is the same as its minor arc measure. So if we have the angle AXB is 120 degrees, then we know that the measurement of that minor arc A to B is also written as 120 degrees. Now, normally we think about a measurement as being in units like inches or feet, but in the case of a circle, we can also use degrees as a distance measurement, but only for arcs. And if the measurement from A to B is 120 degrees, so this measurement around the side can also be called 120 degrees, then the rest of the circle has to add up to a full rotation of 360 degrees. So to find the measurement of our major arc, ACB, we say 360 minus 120 gives us 240 degrees. So this is 240 degrees. Let's look at another type of angle here. So a new type of angle is called an inscribed angle. Inscribed means written inside of. So when we inscribe an angle, it means that the angle touches the outside of the circle. So it has a vertex on the circle. The measurement of angle ABC is not the same as the measurement of the angle that would go through the center. Notice that those two angles are not congruent. So angle ABC is called an inscribed angle. Inscribed angles have measures that are half of their arc measure. So if we start with angle ABC, having a measure of 40 degrees, mark it on the diagram. ABC has a measurement of 40 degrees. Then we know that the measurement of arc AC must be double that. Notice how this angle is much more acute than this angle. This one is much smaller. So I have to do 40 times 2 to get the arc length of 80 degrees. That means that the central angle with the same endpoints on the circle is also double the angle measurement of the inscribed angle. So ABC is half of the central angle, which means that ABC is also half of the arc length, because the central angle equals the arc length. Let's do another example. In this example, we want to find the values of A and B. A is the arc length of PT, PT's arc length. B is an inscribed angle, PRS, inscribed. Okay, so the first thing I'm going to do is say, well, I do have an angle that has P and T. I have PQT. So the measurement of angle PQT is 60 degrees. That means if I multiply it by 2, this is inscribed. So I have to multiply it by 2 to get 120 degrees as the measurement of arc PT. So that is our value for A. So we used this green angle here in order to find green times 2 gave us orange, which would be equal to that orange central angle. It's very important to be able to distinguish the central angles from the inscribed angles. So if A is 120 degrees, then arc PS, right? I need to find PRS as an angle, so I'd like to get a point, an arc PS. So arc PS is 120, but then also 30 more. So that's 150 degrees. In order to get the angle PRS, I have to then divide that by 2. 150 divided by 2 is 75 degrees, and that is our value for B. So if we take our additional arc here, and then we divide it by 2 in order to get this pink angle here. Okay. Now we used a feature here that we haven't formally stated. We said that if we add the orange arc plus the purple arc, it would give us 150 degrees. So let's go ahead and state that formally. The arc addition postulate states that the measure of an arc formed by 2 minor arcs is the sum, so we add them up, of the measures of the 2 arcs. So we can say arc AB plus arc BC equals arc AC. Just like we had for angles and segments, we can do the same thing with arcs. And we can actually prove that if we use the angles. We had angle A, we'll call this X, AXB, plus the measure of angle BXC equals the measure of angle AXC. And those are the central angles that are congruent to those arc lengths. So if we look down at the next section, we're talking about arc length, specifically finding a portion of the circumference. So let's review what is circumference. Circumference is the length all the way around a circle. And circumference comes directly from the radius and pi. Circumference equals 2 pi r. And so if I have a radius, I can always find the circumference. And what it means is that if I had a string, the length of the radius, I could fit just more than 6 of them around the outside of a circle. Because pi is a little bit more than 3, so the circumference is a little bit more than 6 radii. But if I wanted to find a portion of the circumference, let's say that I want to find the part of the circumference cut off by an angle of x degrees. So if this is my central angle and I wanted to find that pink section of the circumference, then I would say arc AB equals the circumference, but times x over 360. Because the pink section is x degrees out of the entire circle, which is 360 degrees. So let's go ahead and apply this. If I want to find the length of arc AC, and the measure of angle AC is 80 degrees, I have the radius, I have an angle measure, and I want to find this pink part of the arc, just the pink part there. So I'm going to need that angle measurement. First, let's find the whole circumference, which is 2 pi r. 2 pi times my radius is 8. That gives me 16 pi. I'm not going to round anything until the very end if I have to. That means arc AC is going to be 16 pi, the circumference, times how much of the circle out of 360 degrees. I have 80 degrees out of 360. So to find this exact value, I'm going to put everything except for the pi in my calculator. So I'll put 16 times 80 over 360. And if I want an exact answer, I'm going to go math, leave it as a fraction. And so we get 32 over 9. So this is 32 over 9. Remember how we left pi out? We need to remember to put it back in. 32/9 pi. If I want to round this, if it says round to the nearest tenths or hundredths or something, I would take 32 over 9 times pi. That will give me 11.17. So this is approximately 11.17. But if you can give an exact answer and it doesn't specify to round, always give the exact answer. In the next example, we're looking at finding arc AD. So be careful. Don't find just the first arc length that you can. I need to find the orange angle in order to find that orange arc length. So I know that these two arcs are congruent. Arc ED has a central angle of 40 degrees. If they're congruent, that means arc AE is also 40 degrees, which means that angle A to the center to E is also 40 degrees. So that angle, if we call this O, AOD, equals 80 degrees, right? We had 40 and 40 to get 80. Our radius is 6, so our circumference is 2 pi r. 2 pi times 6 equals 12 pi. To find our arc, we use the formula circumference times degrees over 360. That's 12x times 80 out of 360. 12 times 80 out of 360 gives us 2.666, which is why we want to look at it as a fraction, and that is 8/3. So that is 8/3 pi. I drew an x instead of a pi. 8/3 pi. Again, only round if you absolutely have to, and always check for units. We haven't had any units in the last couple problems. Let's take a look at our next page. For this part, we are looking at the same thing except for area. So in order to find the area, and I'm going to call this center O with angle X, in order to find the area of this enclosed region, which is called a sector, sector is like a slice of cake or pie. So it's the area enclosed by a central angle. So if I wanted to find that portion of the area, just like we were doing before with circumference, now we're going to do the same thing with area. So the area of a sector, AOB, there's no special symbol for sector, so we just write the word sector AOB. If you have a diagram with only one sector, you can just say area of the sector. So the area of sector AOB is going to be the area of the circle, circle O, times x over 360, just like before, except with area. And remember, area equals pi r squared for a circle. So let's look at our example. Our first part here, find the area of the shaded region. So that is the area we're looking for. To find the area of a circle is pi r squared. That's pi times our radius, which is 12 squared, 144 pi. But I don't want the whole area, I just want the sector. Area of sector equals 144 pi times how much of it do I need? I need 150 degrees out of the 360 degrees that make up a full circle. And so we can say 144 times 150 divided by 360 gives us 60. So this is 60 pi units squared. We don't know the units. On part 2, it's a little bit trickier because the first thing we have to do in order to find this little tiny region in here is find the much larger region of the sector. So we want to find the shaded region. We know that the measure of angle of arc AB is 60 degrees, which means the central angle here is also 60 degrees. And we know that the measurement of CA is 4. So we need the area of the sector, which is the area of the circle times x over 360. Area of a circle is pi r squared times x over 360. Radius is 4. Pi times 4 squared. X is 60 over 360. That is 16 pi. We can actually reduce 60 over 360, 1 over 60. You don't have to reduce it. We're going to put it in the calculator anyway. 16 over 60, or 16 times 1 over 60. Leave it as a fraction, is 4 over 15. So we have 4 over 15 pi. And I've just realized 60 over 360 is not 1 over 60, it's 1 over 6. I said that seems too small. It should be 1 over 6. Let's try that again. 16 over 6 as a fraction is 8/3. That's much better. So not 4 over 15, 8 over 3. 4 over 15 is so tiny, it would be a tiny little sliver. 8 over 3 makes much more sense for a slice of pie this size. Okay, now that's the whole slice of pie, the whole orange sector. We don't want the whole orange sector, we just want the purple part. So now I want to find the area of purple equals area of sector minus the orange part, which is actually a triangle. Notice this is an equilateral triangle here because this is isosceles and that's a 60-degree angle. And so we actually have area of triangle ABC that we need to subtract. How do we find the area of triangle ABC? Of triangle ABC equals 1/2 base times height, which is 1/2. We can use 4 as our base, that's our radius. How do we find our height? Well, if we split an equilateral triangle in half, that creates a 30, 60, 90 triangle. This will be 2, so that this will be 2 root 3. And that gives us a total of 4 root 3 as our area of the triangle. So we have 8 over 3 pi minus 4 root 3. This would be the exact answer. That is pretty messy. So the simplified answer, putting into our calculator, 8 over 3 times pi. Let me try that again. 8 over 3 times pi minus 4 times the square root of 3 is 1.45. So this is exact, and this is rounded. For the next section, we're looking at the special lines that interact with circles. And so our first type of line is a line that touches the circle at only one point. And earlier we said that is called a tangent line. And so if I'm looking for a tangent line, I'm looking for a line that just barely touches the circle in one point. And we can draw a tangent line to any point on the circle. And the point that the tangent line touches the circle is called the point of tangency. And if we connect that point of tangency to the center, we get a radius. And every single tangent line can have a radius that touches its point of tangency. And if we look closely at the radius and the tangent, every radius and tangent has this special relationship that they make a 90-degree angle. They are perpendicular. So any tangent line that I draw will have a radius at its point of tangency to which it is perpendicular. Let's look at some examples. In this example, we have segment ML and segment MN that are tangent to circle O. That means they touch the circle at only one place. The circle is named by its center point, so that means this point here is called O. The two tangent lines have a point M in common. That means that this point is the one that's in common with those tangents. So that's ML and MN. They're tangent to O, find the value of X. Well, we don't have a whole lot of information, but we do know that every tangent line is perpendicular to its radius, and therefore we have a quadrilateral with 3 given angles. We can always find the 4th. If you'll recall, the angle sum for a quadrilateral is always, hopefully you've said it, 360 degrees. And that means that we can add up these angles. We can say 117 plus 90 plus x plus 90 must equal 360 degrees. That means that x is 360 minus 117 minus 90 minus 90. And that gives us an angle sum of 63 degrees, or an angle total of 63 degrees. If you forget the angle sum for a quadrilateral, you can always think of a square or a rectangle has 4 right angles, and 90 times 4 is 360. So that's kind of a quick check for angle sum for a quadrilateral. You can also think that it divides into 2 triangles, and 180 times 2 is also 360. In our next example, we have circle C, and we want to find its diameter. Be careful, because the segment here that's missing a length is a radius, and I need to find a diameter, meaning that the answer we get for side AC is not the answer to the question. So how do we answer this question? Well, we know that the tangent is perpendicular to the radius, and that tells us we have a right triangle, 2 given sides. We can use Pythagorean theorem. Pythagorean theorem is a squared plus b squared equals c squared. Starting with our hypotenuse, that is 18 squared equal to our legs squared. 15 squared plus r squared. Subtract 15 squared. I'll do this part in my calculator. 18 squared minus 15 squared equals 99. So that means that r is plus or minus the square root of 99. It's a distance, so it has to be positive. 99 factors into 9 times 11, which is 3 times 3. So this is 3 times the square root of 11. But again, we didn't want the radius, we want the diameter. Diameter is 2 times the radius. 2 times 3 times the square root of 11 is 6 times the square root of 11. How come I didn't have to distribute here? There's no addition or subtraction. This is just multiplication all the way across. So if I had 2 times 3 times 5, I would say that's 6 times 5. I would not say that's 6 times 2 times 5. Be careful with that. Next, let's look at inscribing. So we said that we had inscribed angles before, and that's an angle that has its vertex on the circle. Well, we can have an inscribed shape as well. And if we have an inscribed quadrilateral, meaning all vertices are on the circumference, kind of wrote through the angle B there, all vertices are on the circumference, then we know that the opposite angles are supplementary. Where this comes from is that if I were to divide this quadrilateral in half, I can see that angle ABC and angle ADC are both inscribed angles, and together they make up the entire circle. And therefore, their angle measures have to add up to enough to give us 360 degrees of arc length. An inscribed angle is half of the arc length, so it should be half of the total circle's arc. The whole circle has an arc length of 360 degrees. So the two angles together have an arc length, or have an angle sum of 180 degrees. If you didn't follow that, that is okay. That's just my explanation of why are these two angles supplementary. So angle B and angle D, they're opposite of each other. These are supplementary. Angle A and angle C, again, opposite, they are supplementary. So let's see if we can find some of these angle measures. I'm going to find 4 things, so I'm going to put them off to the side here so that I make sure that I answer all parts of the question. And I'm going to use colors to help kind of keep track of everything that's going on, because there's a lot going on in this circle. Let's start with angle D. Angle D and angle 100 are across from each other. I don't actually need the color yet. Angle D and this angle that's 100 degrees are across from each other. That means they're supplementary. So D plus 100 should be 180 minus 100 equals 80. D is 80 degrees. I can do the same thing for angle C. These two angles are across from each other. So C plus 96 equals 180 minus 96 gives us 84. So C is 84 degrees. Where the colors are going to come in handy is looking at these arc lengths in order to find A and B. And the reason I find the colors handy is because we're going to be looking at the same segments and segments that go past the end of certain vertices. So notice I have an arc length here of 99, but that arc length doesn't have an inscribed angle. The closest arc length that I can find that inscribes that angle includes part A as well. And the angle that's inscribed there is 100 degrees. An inscribed angle is half of the arc length, and that means that this arc length is 100 times 2, 200 degrees. And that tells me that if I add up my two arcs here, it should be 200 degrees. So 99 plus A equals 200, minus 99 is 101. A is 101 degrees. Now that I have A, 101 degrees, I can use that in order to find arc length B by finding a new inscribed angle there as well. And so again, we're going to use the idea that the inscribed angle is half of the arc length. So if the angle is 84, then the arc length is 168. 84 times 2 is 168. And so I can say arc length A plus arc length B equals 168 degrees. Luckily, we have arc length A, so that's 101 plus B equals 168 minus 101 equals 67. And there are our 4 parts of our solution. Let's take a look at the next page. This is the last problem of the section, and so I'd like you to go ahead and give it a try, and then we'll go through it together. So just like the last one, I'm going to start by finding the interior angles here. So I know that A and 68 need to be supplementary. A plus 68 equals 180, minus 68 equals 112 degrees. A, B, and C are what I'm looking for. A is 112 degrees. And then again, using colors, I'll use different colors this time. I have the given arc is 104, but I don't have an angle until I get to the end of including arc C. My inscribed angle is 71, which means double that for the arc length to get 142 degrees. 71 times 2 is 142. 142. So then I can say 104 plus C equals 142 minus 104 equals 38. So angles, or arc C is 38 degrees. And then we still need arc B, so I'd like to find arc B. And as much as I can, I want to overlap what we know in order to get our inscribed angle here. And so 112 times 2 equals 224. That tells me 142 plus B, the entire orange arc there, equals 224 minus 142 equals 82 degrees. So B is 82 degrees. Okay, that's it for this notes video. That's the end of the videos for the week. Your test is tomorrow, and we'll have time to review and ask questions just like our normal Friday routine.